think we'll go ahead and get started on our next Ivan Roundtable workshop, Fraction Libraries for Quantitative NMR Metabolomics. At this time, I will pass it over to Krish.
Thank you, Eric. Welcome, everyone. Happy New Year. I will introduce today's topic. Today, we have Professor Art Edison from University of Georgia. He is going to talk on fraction libraries for quantitative NMR metabolomics. Interesting. We have always talked a lot about metabolomics in the past. So looking forward to this. I think without any further ado, Art, the floor is yours.
Great. Thank you so much for the invitation. I'm really honored and excited to be here. Thanks, Krish and Eric and everybody for helping to organize this and everybody for showing up. So I'm going to tell you about the latest thing that we've got going in our lab and in collaboration, especially with Frank Delaglio at NIST, on using metabolite fraction libraries. I think that this, I hope to show you the utility of these things. But before I jump into it, I want to advertise, if you will, this new thing that we've got that the University of Georgia partnered with UConn, Jeff Hoke, and NMR FAM, Katie Hensler-Wildman, and Chad Rienstra. We partnered to create this thing that we call the Network for Advanced NMR. And this was funded by the National Science Foundation through a major or a mid-scale research infrastructure grant a few years ago. And in that grant, we were able to get two 1.1 gigahertz NMR spectrometers, one located right here at the CCRC and at the University of Georgia that's dedicated to liquids, and one at the University of Wisconsin that's dedicated largely to biosolids and materials. And all of these instruments, along with the associated instruments in each of these facilities, are networked directly to UConn, where we have a nice platform to harvest the data as it comes off of all of our instruments, and it goes up to a server at UConn, where it then is stored and made accessible. We can do a lot with that in this server. You can download data. If you're collecting data, you can go to UConn if you want to collect data at either of these facilities. You can put it right into NMR Box to start processing and analyzing it. So it's a nice setup. And the biggest thing that I want to bring your attention to is that, this is our facility at the CCRC before I jump into how you can use this. So we've got we have several 600s, but we also have this 800. They're all Brooker Neo consoles right now, 1.7 millimeter cryoprobe, so specialized for small volume samples. All of the data that I'm going to show today, by the way, is collected on that instrument. We have an older one of the spaceship 900 megahertz that's been updated to a Neo console, and some great C13 detection capabilities on that. And then the 1.1 is the centerpiece right now with a good carbon detected cryoprobe, carbon and nitrogen, and a TCI cryoprobe in it. And it also has a sample jet sample changer. So these are all available to all of you as a facility. And the big thing is that for expert users, you could just send us samples, any of our facility. You can just contact us and you send samples. We can get the samples in. You can just run samples from your desktop remotely, and data are put onto NMR, the NMR Hub resource there. So please contact us if you're interested in this. It's, the prices are just what we pay for academic users. We charge more for industrial, but you're welcome to do it. You can also come in person, but for people who know what they're doing, this is oftentimes a nice way to do it. Okay, so that's NAN. I just wanted to make sure that everybody was aware of this resource, and we'd like to have you come and join us. I'm going to really be talking about metabolomics today, and I know not everybody in the audience is familiar with metabolomics. So I'm just going to give a little summary of what it means. Means different things to different people, I think, but in general, we take this rather complicated pathway. This is the KEGG pathway in this case of lots and lots of metabolites and try to make some sense of it. So normally we are working with two groups in its simplest form, a control group and a test group, where it might be a population of people that are sick or a plant that has a genetic mutation compared to a normal or different environmental conditions. So we want to compare two groups. And the aspirational goal is to essentially identify and quantify everything in a study, all of the metabolites in a study that are relevant to the test versus the control. And currently that is impossible because no technology can actually detect all of the metabolites, and it's also very difficult to quantify all, and not all of them have been identified in general. So there are two main technologies that are used for metabolomics these days. There are other things that are possible that I'm not going to be talking about, but the major ones are NMR and mass spec. And mass spec is really, in many ways, dominating the field these days because of the sensitivity that it affords and the number of signals that it can measure. And I'm just indicating in this slide sort of my comparison, the way I think about these two technologies. First of all, I consider them complementary. We use mass spec a lot in our work. We use more NMR, but mass spec has a lot to offer. And the way I'm ordering this list of different properties is the ones at the top are really good for NMR. The ones at the bottom are really good for mass spec. And we all know that NMR is non-destructive, so you can make a measurement, you can put it into mass spec, and then you can get an additional measurement. NMR or mass spec is super sensitive, as I mentioned before. Something that we don't often brag about, I think, in the NMR field, although this is coming out more and more in AI type things, but NMR is highly computable. So all of the parameters that we measure, chemical shift couplings, and so forth, we can compute these from first principles in many ways, in many situations. And so it really lends itself nicely to machine learning, AI kind of applications in a way that mass spec, fragmentation patterns, and chromatography is not quite as good at that. NMR can be quite quantitative. I'll be addressing that more during this talk. NMR is highly reproducible and so forth. So structural information, both methods can get at that. NMR is certainly an advantage in that case. The three areas that I think are super important that mass spec does very well and that NMR may be a little bit harder are these. So sensitivity is an issue for NMR. Sometimes overlapping of signals are an issue. Mass spec can avoid a lot of that because they routinely use chromatography in LCMS at least. And then mass spec the databases are much more established right now than NMR databases. So I'm going to be addressing all of these things and with some suggestions on how this approach might improve these. Okay, so I'm going to next define the problem that we face in NMR metabolomics. And I'm going to illustrate this with an NMR spectrum from a filamentous fungus called Neurospora crassa that our lab works on with Jonathan Arnold, a colleague of ours. And we study this organism for many reasons that I'm not going to be talking about today in this talk, but the most interesting one is that it undergoes circadian oscillation, and it's a single cell organism, and so it's a nice model system to study clock behavior in a simple filamentous fungus. But this is an NMR spectrum similar to the kind of thing that we would get in a lot of other samples, and that a lot of you have probably seen, of a mixture of metabolites this is a polar extract of Neurospora crassa. And there are a few things I want to bring to your attention. Obviously, on the left, we don't have a very high concentration, in this case, of aromatic sort of compounds. On the right, we have more, a lot of sugars and some other other peaks in there. I'm just going to zoom into this little region right here. And this is the sort of thing that we deal with all the time in NMR metabolomics, where we have a 1D proton spectrum. We have lots of little peaks in here, lots of some big peaks, and then we have these things that, if you can see my cursor, little teeny peaks in here that frankly, we oftentimes just end up having to ignore because they're either overlapped. We're not sure if they're real, what's going on. And there are a lot of methods to dig through this, but it's still a problem to try to actually get quantitative information out of this kind of a spectrum. And the type of thing that we would like to be able to do is shown here, where, for example, like branched chain amino acids are relatively easy to pick out in the methyl region. So here's valine. You can get a database spectrum of valine. You can see somewhere in here would be the alpha proton for valine. A little bit hard to see these things, but in these crowded regions, the methyls are nice, but not all metabolites have clean methyls like for valine or isoleucine. So here's isoleucine, here's GABA, here's ornithine, here's alpha ketoglutarate, here's malate, and here's an unknown, this gold one. And so the question that you should be asking right now is, first of all, how am I making this claim that these are the right identity? Now, there are various approaches that people can use for this, various database matching or direct fitting of NMR data, but it can be fairly complicated. Just before I forget to bring this up, I do want to say that we use 2D NMR in my lab all the time, but I'm not going to be talking about 2D NMR at all in this talk. So don't come away with the impression that we don't like 2D NMR, because we do. But it's really not practical to profile hundreds or many hundreds of samples in a metabolomic study on every sample. So you want to know, how are these identified, and then and overlap really makes quantification of these things a challenge. We like to say that NMR is quantitative, but faced with a spectrum that's like this, it's really hard to know exactly what that means or how to do it right. And then further, you should be asking yourself, how do I'm giving this spectrum here for an unknown compound. How am I telling you that it's unknown? And let me also define right now what I mean by unknown. What I mean is that it's not in a readily available database that we can match. I'm not at all supposing that this is something that is a brand new compound to science, but it's not accessible in a database. And so I'll get to that as the talk progresses. Okay, so there are different types of analysis that you can do with a data set like the one that I just showed, if you have a bunch of them for a couple of different cases. And this is nicely illustrated by this. This is, if you Google this fellow's name, Sven Sack-Salber, I guess is the pronunciation. He's a performance artist who literally went through that haystack on the left of our screen to find a needle. And so he found a needle in a haystack in an art gallery, and that's what he did to do complicated analysis. He ended up finding it. There's a video of him finding it. It's interesting. But anyway, so I'm going to highlight the different approaches that, in a big picture sense, about what we can do to sort out the needle from the haystack in NMR metabolomics. So these are a couple of spectra that Chris Esselman simulated from library samples from Gizmo, which we love, a data set based on fitting the spin system to BMRB data or other data. And Chris has simulated two different groups, group 1 and group 2, and put 3 different replicates for each one. So this is just a simulation to show the concept here. And so in NMR metabolomics, we want to know something about the difference between these things. You can take the approach that's widely popular, and we've used quite a lot in our lab, chemometric approach, where you just essentially take the data, and before you make any effort to try to analyze the data or identify the data, you see what's important to the study. So if you do something like a PCA analysis, you get two different group structures. You can take, once you have this, you can take the loadings plot across the component that separates these things and see what signatures in what NMR peaks in this spectra account for that difference. So this is a powerful method to hone your attention on the stuff that actually matters for the study. But there's an alternative, and the alternative I'm going to illustrate through this cluster that's highlighted on the left, and that's blown up here. So here's a mixture from that peak, the peak area that I just showed. The black is the trace that we just saw. And it's a mixture, and in this case, Chris knows what he put into the mixture: ornithine, lysine, arginine, and GABA. And so the sum of all of these components make up that black trace that we saw. So this makes for a beautiful sort of presentation, and it's very appealing to say, oh, I can see how these all add together to get the peak, and I can quantify everything. But to do this is still quite a struggle. And most important, if there are unknown compounds that are not represented in databases that we don't have reference spectra for, then that really becomes more and more problematic in this type of approach. So the database problem can be summarized with this kind of drawing. So here's this red dot represents the measured data in a particular study, and the blue might be a database that we try to access to try to match our data to the database. And at least in our hands, oftentimes 50% is kind of generous. We're often at 30% matches or something like that, but it's certainly not 100% of all of the compounds. All of the peaks that we measure are not in databases typically. So this is a problem. And then if that particular peak that we're trying to fit doesn't have a database match, then that becomes a problem. So they don't fully cover the observed data. We could take the approach of let's just build bigger databases. That's a nice idea, but there are so many compounds out there, it's going to take a lot longer than any of us have before the databases get big enough to make this work. But at the same time, it's also creating a problem. So the bigger the databases get, the greater the number of false discoveries that you're going to have when you're matching to them. So there's not a really simple way out of this problem with the way we're currently doing it. And what I'm going to show you in the rest of the talk is an alternative that I think really makes a lot of sense given this kind of difficulty. Okay, so the bulk of all the rest of the time, I'm going to focus on this new approach that we call metabolite fraction libraries, and you can go find all of the details of what I'm presenting now at this bioarchive, where there's a link shown here. You can search just Chris Esselman or my name, Art Edison, on bioarchive and find it. So it's just summarized here in this one picture, and then I'm going to go through these components in more detail as I go. So the first step is that, well, we start with a study of a bunch of different samples. So these individual tubes with blue or red dots represent tubes or samples in a study. We would profile all of these with a 1D proton NMR spectrum. We always collect 2DJ spectra in these protocols as well, but I'm not showing any 2DJ analysis. And then we always make pooled samples for quality control in our metabolomic studies, where we'll typically do 2D NMR and also make sure that everything is working right in terms of this internal pooled sample. But in this case, what we're also doing is take these pooled study samples into a single pooled sample here. Then this is going to be injected onto an HPLC, just a semi-preparative HPLC, and then NMR data recorded. And I'll go over the details of that as we go. And then to process this, we use this technique that that we developed with Frank Delaglio and Chris recently called SAND. I'll just summarize that for a minute or two in the next slide or two. And so this is what I'm calling a metabolite fraction library. The next step is something that is as far as we know, unique right now. And this is, I'm referring to this as the metabolite basis set right here. So we derive from the fraction library, we find unique compounds that comprise a basis set. I'll show you how we do that. And Chris wrote software called Fraction Library Analyzer that is used to do that in currently a semi-automatic way, but Chris is trying to find ways of actually getting that more automated now. Finally, we take these metabolite basis set elements and we fit them to profiling data using Tim Ebel's package called Batman, which is a Bayesian method to fit reference library spectra into quantitatively fit NMR data. There are other Bayesian approaches out there but we decided to work with Batman because it seemed to be well suited to this situation. So that's what I'm going to go through now is further definition of these steps. So here is the neurosperk the same neurosperk extract that I showed you before. This is collected on our 800 megahertz with a 1.7 millimeter cryoprobe. And so the concept here is that so on the vertical axis are the HPLC fractions. So we collect 140 fractions and then do as many injections of the reference standard as we want to try to get more and more material in there. And so the material is collected in the same tubes, then the tubes are dried after the HPLC and then brought up in an NMR buffer, and we collect the NMR data. So the black trace on the back, on the upper row, is the unfractionated material. The trace on the left here is the total ion chromatogram. We have an HPLC that has a single quad mass spec detector, just so we can see clearly what we have going on at every point. And so there are a few things that I want to bring to your attention about this fraction library. One is so if you, for example, well, the bottom line is that we have way more overlap, I think, than many of us even realize. We all know that these black profiling spectra in the back are overlapped, but you can reveal so much overlap that I was surprised when I first saw this. So, for example, this peak down here, beautiful peak down around fraction 40 or so, totally obliterated if you just look at it in the 1D spectrum through this stuff up here. Similar sort of thing with this group right here, but you can see a pattern of peaks on the right side of this box 2 and the left side of this box 2 that look like they're probably highly correlated. You can find other regions actually too that are highly correlated with this. But then these things are obscured if you look up by a different set of overlapping components. So it's very difficult to pull those kind of correlations, even with methods like Jeremy Nicholson's Stocksy, which we use a lot in this approach. It's hard to see that up there. I like to highlight this peak up here. If I saw this, I'd say, "Ooh, that doesn't look like it's either phased well or it's not shimmed well or something's going on." And then you just see that it's just the pattern of overlap that you can reveal with this that leads to that rather ugly looking peak shape at the top. And then finally, in the bottom right corner, addresses these little teeny peaks. And you can see that basically the question, so you can see all of these peaks coming out. You can often see correlations with those peaks. So suddenly those little blips that I brought your attention to up here in the unfractionated material, those become something that you can actually start to analyze. And to give you an idea of the sensitivity of this approach, I'm highlighting a peak that's not actually shown in this right here, but we're taking a free histidine in that Chris had that wasn't overlapped, and in the mixture, the histidine resonance in the mixture is shown right here, and we also have DSS in every one of these spectra at a known concentration. And so when Chris integrates this peak compared to the DSS in that, he gets 170 micromolar of histidine. But we can also see that elute over the fractions, with concentrations shown here, everywhere from 27 micromolar up to 1100 micromolar. And the reason, well, it turns out that the sum is about the same proportion. We're putting in, I guess, about 15-fold. Actually, I'm not doing the math in my head just right, but the amount of excess mass that we put into the HPLC, we re-inject and re-inject and rejected, compared to the unfractionated mixture, turned out to be exactly the same proportion. So we're recovering most of the material, at least for the histidine, and you can get a sensitivity boost just by multiple injections. Okay, so let me just go back and also state that the peaks that are shown in here have been processed with this method called SAND, which is really inspired by Kraft from Krish, and then Frank helped us make this into something that has become really useful for our lab. And so again, let me just say right at the start that when I say inspired by Kraft, it's basically doing what Kraft does and no better in terms of the results. But what we were able to do is, with a single command line in NMR box, is with just one command line we can process the whole data. So that entire fraction library was processed by Chris over just a little bit of, just a single line commands for every step. But the approach that we take, it's been published, so I'm going to go over this rather quickly, but you can look at this in analytical chemistry. But the general idea is that take a Fourier transform initially to define regions of interest that have, like, say, 3 to 5 peaks in them. And then we cut those peaks out and make a bucket. And then that bucket is inverse Fourier transformed and separated into a training set and a validation set of data. And the reason that we have to do this is just too computationally intensive to try to fit the entire spectrum in the time domain. So we break it into these little parts. So we subsample this, and then we optimize. We basically fit NMR signals to this. The frequency, decay, amplitude, and phase. But we start with a phase spectrum, so we usually just the phase doesn't enter into the optimization. It's just zero. And then we optimize for how many signals are in there to best fit the data. And we can do that with the training set and validation set, compare those results. We can see the RMSD go down, and if it goes down and then levels off, then we know that we have reached the optimal number of signals in that bucket. We get what Krish has termed, and what we're loving these days, is a tabular domain data set, where we have just the list of frequencies, decay, and amplitude, and we have something that looks like these 3 separate Lorentzians that represent that bucket to begin with. So that's SAND in a nutshell. And now the essentially here, I'll let you look at the publication for more detail, but it does a pretty much perfect representation of the chemical shift in a simulated data set where we knew the answer and compared what we got out of SAND. Amplitude was really good if for non-overlapped regions it starts to decline a little bit for highly overlapped regions, and then the line width is also nicely fit, and it starts to become less dependable in super overlapped regions. But generally, SAND does a nice job. So these panels B and C are different regions of a simulated spectra, where the black is the Fourier transform of the data, the red is the sanded reconstruction of the data, The green are what we put in as ground truth peaks, and then the blue are what SAND was able to estimate. So there's some places like here, for example, where SAND guessed that there were 2 peaks under there and we had only put in 1. But most of the time, it's a pretty good representation of what's actually in the sample, in the spectrum. And now I'm showing a small little region of fraction 110 from our fraction library that Chris did. So so he sanded every one of the fractions in there, and you can see on the back is the black trace is the Fourier transform, the red one is from sand, and then in blue are the individual Lorentzians that make up those complicated peak shapes from that. So that's just to say that fraction library has a lot of work in terms of already deconvoluting all of the peaks. Okay, so what do we do with this? This is a different view of the fraction library, and I'm going to walk you through how we make this metabolite basis set element. And what we do, this is embodied by this fraction library analyzer that Chris wrote. So if you focus your attention down here on panel A, this is just a different sort of view of a different region of the fraction library. And you can see, so we just have a subset of the fractions and an expansion of some of the chemical shift range. You can see that you can identify peaks that are eluding across the fractions, and then you can see these patterns of coelution. So it won't be a big stretch of the imagination to realize that these traces that look correlated by eye are essentially perfectly correlated when you do the correlations across the fraction. So what Chris does is starts off at the first occurrence of a peak, and then follows that peak all the way through to when it goes away, and then he finds all of the other peaks in the fraction library that are highly correlated to that. And so this is trace 1 versus trace 2. So this versus this. The middle one is trace 1 versus 3. The right-hand correlation is 2 versus 3. And these are essentially perfect correlations of the different components of a molecule eluting over fractions. And so this is very similar to Stocksy, Jeremy Nicholson Stocksy. The only difference is that in this case we can put a threshold of, we usually in practice use a threshold of 0.98 to start with for correlation, and if they exceed that, then we say, okay, it's probably a molecule. And then we call those correlated peaks a metabolite basis set element. So in this case, this is metabolite basis element indexed N. And then you can search databases. In this case, we searched the Gizmo database for that element, and we find essentially a perfect match to glutamine. So we say, well, that's a good candidate for glutamine. And then what we do next, and I should say that the way we do this is through the Brushweiler Labs implementation through Colmar 1D of the Gizmo database, which really is effective in what we're doing. So we love that combination approach. But after we get this metabolite basis set element N defined, then we can take that out of the fraction library. This is the advantage of the tabular domain data. So we can find these peaks that were highly correlated. And if you look over on the right-hand one, you see that where those red arrows are, we've removed those from this fraction library. So this is everything that was shown on the left, but without that metabolite, without glutamine in it. And so then we just go to the next peak of interest and keep on repeating this until essentially we remove all of the signals from that fraction library. So this is how we construct what we're calling the metabolite basis set of the sample. So this is what it looks like. This is the metabolite basis set for that study, the neurospectracid metabolite basis set. This looks like the fraction library, but it's not. It's ordered by the highest amplitude that we were able to see in the fraction library is on the back to the smallest amplitude on the front. And basically, each one of these things represents a metabolite basis set from the correlated peaks in the fraction library. So these are all separate, highly correlated peaks. The bars here indicate that the left-hand black bars indicate good matches through Colmar 1D and Gizmo. The gray ones, ambiguous matches. The red ones didn't show up at all. And so you can see this is how we get these names in the case in my introduction slide, including the unknowns. So when we have an unknown basis set element, we can use that in fitting data that I'm going to show you on the next step. The key here is that this metabolite basis set is our database. So we have no need at this point to, except for to match what these identities are through Colmar or other databases, we don't have a need anymore to use an external database to fit our sample. We can use the sample-specific database to fit our sample. That's really the whole thing. So this is the database. It includes both knowns and unknowns. So now what I'm going to be showing during the last bit of this talk is what we do with that database. And this is where Batman comes in, Tim Ebel's program that does Bayesian fitting of database libraries. But in our case, the database is our metabolite basis set. So we're taking here, I'm switching gears and I'm showing a experimental ground truth spectrum of 53 metabolites. And we made 10 different mixtures of these 53 metabolites. One of them is shown up here on the top in the black NMR spectrum. The red below that are the metabolite basis set elements for this ground truth spectrum that we have. We went through the whole fraction library and metabolite basis set for this synthetic study. This red spectrum is the derived metabolite basis set representation of the black study, and then the blue is the residual that's not fit perfectly well. And so a few things to see from this data. First of all, we're defining a percent quantified of the black spectrum as the square of the residual, so down at 1 minus the square of the residual divided by the square of the spectrum times 100. That's the percent quantified. So for this spectrum, Chris and Kara are able to quantify 96% of that spectrum. Now, I mentioned that there are 10 different mixtures of the synthetic spectra. There were a few compounds, and one shown down here that didn't have overlap in the resulting spectrum, and Chris was able to do a standard integration compared to the DSS that's in every sample of all of these compounds, comparing them to the Batman derived concentrations, and they're basically very good. They're very high correlations, except for something like histidine, for example, where it could be improved. And what we know now is that the histidine has, as all of you know, has a lot of pH dependence. And so this is a pH shift that wasn't accounted for. We didn't let the histidine resonance move enough in this fit. So we have to still work a little bit more on highly pH labile sort of compounds. But in general, we get really good agreement with integrated values for all of these things. And the question then in this mixture is what happens if we leave components out? So the same one that I showed you before, now we're leaving out the top 10 basis set elements that we were able to derive from that mixture. So we're just leaving these things out of the fit, refitting, and we have the same percent quantified. In this case, it goes down to 82% from 96. So you can see that there are regions of the residual that don't fit very well right now. And if you look carefully, you'll see that in all cases, they're explained by the missing database or the missing metabolite basis set element shown below. So that's if we leave 10 out. If we leave top 20 out, we reduce the fit quality to 56%. So this basically just shows that this seems to be behave as you might expect if you have fewer and fewer basis set elements to fit into the data. So finally, the last bit of data that I'm going to show is back to this Neuraspora crassa. What can we do with that? And that's shown here. So the NMR spectrum is shown that the unfractionated profile spectrum is on the top. And this is the aromatic region. This is the aliphatic region expanded. And Chris gets about 94% for this fit of the using the Neuraspora crassa derived metabolite basis set element. So it works quite well in a biological sample. And then we said, well, we have two different basis set elements, one for Neuraspora crassa, one for this standard mixture. What happens if we switch them? And so if we switch them back and forth, then on the top we have Neuraspora crassa being fit by the synthetic standard basis set. We get about 83% fit, and if we take the ground truth synthetic data set and fit it with Neuraspora crassa, about the same, 82%. So neither one is as good as being fit by its own basis set element in this case. Okay, so that concludes an overview of this presentation about using metabolite fraction libraries for quantitative NMR. The summary is that basically, we know that NMR metabolomics is overlapped, and it surprised me how overlapped it is. You can see that clearly from chromatography. Chromatography can reduce overlap, increase sensitivity, provide samples for mass spec. So we can take those physical samples of those fractions and then do MS. We can do functional testing, other sorts of things. And then these metabolite basis sets that are derived from that are really useful for a database independent matching of profiling data using both known and unknown metabolites. So and I should just emphasize that you just do this what looks like a lot of work. It takes a couple of weeks of work up front. So but you only do this once for each kind of study that you're working on. So I think it's still a feasible sort of approach. So with that, I want to thank the NSF for NAN and also helping with this fraction library. NIH through a MIRA award has funded a lot of the fraction library. NAN and my colleagues at NAN, the folks who got SAND working, UA especially, and Frank Delaglio and Krish and others. Metabolite fraction library really has been largely Chris with a lot of other very helpful input. And then I do want to point out that Oscar Millett heard an earlier version of this talk, and he actually had the insight to say, you can do more with this, and got us thinking about this fitting of the data. So with that, I want to thank you for your attention and happy to answer questions.
Thanks, Art. There are a few questions in the chat room. I'm going to call out the people who sent a question.
Should I stop sharing, Krish? I'll stop sharing.
No, you can keep it because the question has.
I want to go back.
Yeah.
Okay, great.
So for the first question is from Peter Merau. Peter, are you here? Yeah, I see your name. Can you unmute and ask the question, please?
Yeah, I was just looking at the fraction plot and thinking that looks like a lot like a DOSY spectrum. So could you use the same approach with DOSY to try and develop this basis library?
That's a really good question. I think the answer is probably yes, to the extent that DOSY separates by just diffusion instead of interaction with the column. But it seems, frankly, we've used DOSY a little bit, but not a lot. And I never have gotten, sort of as good a separations as with chromatography. But basically, I see no reason why not. might be thinking about it or missing something, but it seems like it's an intriguing idea. Might be worth a try.
Thank you.
Sure.
Okay. I'm going to go slightly non-chronological order in these questions. I'm going to request Kalindi Morgan, which is similar question to what Peter just asked. So maybe we can give Kalindi a chance. Could you please unmute yourself and ask the question?
Yeah, I guess I was thinking, I mean, chromatography is great, but then, so for instance, you're going to be producing a lot of samples that, right, have to be put through the NMR. And it is really interesting to see how you get that separation. We can start seeing what was overlapped, not the overlapped. And, but from, so thinking about the DOSY, I don't know if you're familiar with Frank Schroeder's work, because he's done a lot of work with DOSY and natural products, and how
We've worked with Frank a lot. Yeah.
okay. That reminded me. But I also, so my own working with fractions in NMR, I've noticed that sometimes HSQC and then an HSQC toxi can help, right? You start getting some separation in the 2D. And I just wonder if a person couldn't, for instance, make 140 fractions on their HPLC and then put that onto NMR, if you think there'd be a way to integrate some 2D data into.
Yeah, that's a good question. And sort of my disclaimer at the start, we are certainly not anti-2D. We use 2D all the time. So and a lot of the separation that you get, you of course realize that you would see if we took the same sample and do a toxi or other 2D experiment, we would see considerably less overlap. That's what 2D NMR is for. The way that we plan on integrating 2D into this is basically we still have all of these fractions left after we're done recording the 1D spectra on the fraction libraries. And then if we find metabolite basis set elements that look really interesting that we don't know, that don't match databases, then those are the ones that those fractions that are enriched in those basis set elements would be the ones that would be candidates for full 2D analysis and, HSQC, HMBC, blah, 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 all of the 2Ds that we would use to try to characterize a natural product. So that's the approach that we've taken. We have, by the way, we have the 2D JRes data for every fraction as well, and we have made some progress on actually just creating the JRes fraction library. Some huge advantages in that, just because you get rid of the coupling, but then you're just working with the projection of the JRes to make this thing. So we're still fine tuning how to think about that. But those are all good suggestions. Yeah.
Well, it just makes more sense especially with HSQC toxi, because you end up pulling out spin systems a little bit, right?
Yep. Totally agree.
I don't know.
Yeah. Yeah. In fact, we oftentimes go to Colmar, not the Colmar 1D, but Raphael has a lot of facilities in there for HSQC toxi and other kinds of experiments to pull out those correlations. I agree completely.
Well, thank you so much for an interesting talk, a lot for me to think about. So,
Thanks.
Next question is from Matt Merritt. Matt, do you want to ask your question?
Sure. Art, I'm still sitting in your office. So,
hey, Matt. Yeah, you're trespassing, I think.
No, my question was about you selecting part of the Fourier transform and then doing the inverse transform. But when you stack everything up with a fast Fourier transform, the tails of your peaks kind of go out to infinity. So the inverse Fourier transform is kind of sometimes it's the best we can do. But do you think that may be related to why there's some trouble you have when you get some overlap peaks? Is that you don't have a really good handle on the tails that's happening there?
I'll start by hacking my way through this, and I did see Frank Delaglio is on the call as well, and so he might want to chime in to either save me or correct whatever I say. So the places the data that I showed where the sand got it a little bit off was actually not experimental data NMR data, but mixtures created from the Gizmo library, but it went through the same thing. So your point is still valid that it could be going through those steps of inverse Fourier transform and so on. I'm not sure that the inverse Fourier transform is the problem. I think that the well, I first want to just say that we would love to avoid doing that because it would be a lot cleaner just to take the entire thing and not have to first bin it. But it already is a very computationally intensive process. We use a lot of NMR box time when we're doing a lot of this um, sanding, but but the but I don't think that we've seen evidence that those tails kind of screw up the modeling of the peak. I think what they do though is the baseline. Like if you notice, I'll see if I can pull this up. Uh, the okay, you notice like right here, this is again that modeled synthetic data. The Fourier transform is up here above, and then the sanded result is right here below. It's actually that's actually a baseline offset that we get from that. That's not trying to pull it down and make it clearer to see it. It's what we get, and it's because the Fourier transform baseline oftentimes doesn't go down to zero, but we enforce each one of the sanded components to reach zero. So I think that you're right, but I'm not sure that it leads to the kind of artifacts that you're imagining. But Frank should probably jump in if he wants to add something to that.
Thanks. And Art, what an excellent presentation. Thank you.
Thank
So,
you.
yeah, it's a great question. I would say that the critical limitation is intrinsic to the data, not so much any artifact with performing an inverse Fourier transform on a region of the data, because there are spectral features that overlap almost completely, and there's no way to resolve them.
Yeah.
Except with a procedure like this that pulls spectral signals apart according to some property of the molecules that they belong to. So the fractionation approach doesn't just simplify the spectra, but in addition, because generally molecular signals will be from one molecule will be present in a series of adjacent fractions, we have correlation information that allows us to pull together all the signals that belong to the same molecule. So DOSY does this but at probably a greatly decreased resolution compared to what you can get from chromatography. And 2D proton carbon HSQC performs this separation, but it doesn't group the signals together according to which molecule that they belong to. So there are intrinsic details of overlap and also how to associate all the signals from one molecule together that all have to be dealt with kind of simultaneously to come up with a complete analysis. So that's a kind of long-winded answer. I don't know if it
well, and
is
as the previous
satisfactory.
question, yeah, I was just going to jump in, and as the previous question pointed out, you could add a toxi onto the HSQC and get that information as well, but then that's a carbon selected, so you're not seeing the entire spin system, proton spin system necessarily. So,
Yeah, great talk, Art. Thank you, and thank you,
thanks,
Frank.
Matt. Thanks for the question and for being here.
If I may chime in on this topic as well, in the very early stages in craft, we observed something very similar. So what we in craft we do is even if you have a contiguous regions of interest, we essentially do a digital filter, but we use a digital filter that is 3 times wider than the region of interest. So every peak and then we do a Bayesian, and post-Bayesian, we take away the transition, what we call a transition band of the digital filter. So essentially, only 1/3 of the digitally filtered region is in the pass band, and the rest of them we consider that to be transition band. But what the price you pay is pretty much every peak is decimated 3 times, because your digital filter is 3 times the width of the peak of region of interest. So you end up paying the price in time, but you are focusing the peaks of interest in a narrow transition band of a wider digitally filtered region. And that works extremely well. We actually did a quick test on subtracting the digitally filtered spectrum from the original spectrum and look for how good it has retained the amplitude, phase, and frequencies. And so that's published in one of our papers in the past. So it is a balance of computational time and how you strategically avoid these tails from a frequency domain. So we don't. Craft doesn't never takes the frequency domain spectrum as a source for regions of interest. We just go straight to the FID.
Right. Yeah. Thank you, Krish. I should also just point out that we're always assuming a perfect Lorentzian line shape in this, which is not often perfect. So, and Frank has thought quite a lot about trying to add other types of line shapes that are often seen.
I just wanted to add, it's not just often, most of the time, it is not Lorentzian.
Yeah.
Almost 99+5 is never Lorentzian.
Something very clever that Chris Esselman did in this approach is to pre-process the data with reference deconvolution, so that the line shapes are closer to ideal Lorentzians before sand is applied.
Yeah, I should have pointed out that that reference deconvolution is really useful in this situation, and some of the artifacts that show up a lot with reference deconvolution get minimized with the sand approach. So it's worth revisiting that if you haven't tried it for a while.
Okay, so the next question is from Max Colana. Could you please unmute yourself and ask the questions on the metabolite spaces set?
Sure thing. Hi, Art. Good to see
Max.
you.
How you doing?
Good. Great presentation, and great to see how far along all this fraction library stuff has come. Really impressive. My first had a quick kind of technical question, which was when you're establishing the basis set, the metabolite basis set, when you're calculating those correlations, are you doing those on the amplitudes of the experimental peaks or the the sand determined peaks that you've generated from there?
The sand peaks. Once the fraction library is sanded, then the sand peaks are what we go with, and it becomes nice because you can use either the amplitude. Well, you get the amplitude from the sand peak. And
Right.
Now I should just say that Chris should feel free to anytime correct me, unmute if I'm saying something wrong about that.
No, very cool.
Yeah, we calculate the correlation of the sum of the sand peaks.
Okay.
So
it's the reconstructed features of the spectrum, but not the individual Lorentzians that you are pulling out with.
Right, not from the tabular domain directly. Yeah.
Gotcha. Okay. No, that makes a lot of sense. And I had just one additional question that I thought of between typing my original one and now, which is, have you guys looked at the reusability of these metabolite basis sets for subsequent studies in, say, the same matrix, down the line? Obviously, that's probably a big question that still you're looking at. But I was curious what the outlook for that
Yeah,
is.
no, excellent question. And yes, we're super interested in that. I mean, so we're actually working on a urine study at the moment, but we made a urine fraction library out of a different sourced pooled sample, an external pooled sample. And so we're going to be sort of testing that right now. That's a human urine derived database, but not from the study. So that will partially answer that question. But we're really interested in this. We're also trying to figure out what to do with these basis set elements. I think that they're valuable. They're all derived data from they're not directly measured experimentally, but put through several layers of data analysis to get to that point. But I think that there's a lot of value in having a single place where all of these metabolite basis set libraries are collected and then start to see overlap between these things from different organisms. You could imagine sort of getting into a GMPS-like thing where with mass spec, where you look at MS fragmentation patterns from all sorts of different organisms and find similarities. So I think that the same kind of principle could come into play, but we have to figure out how to do that. And
Yeah.
ideas are welcome from anybody.
Absolutely, yeah. Because I was just thinking, it kind of reminded me of, when you use tools like Batman, you kind of already have to pre-select the matrix that you're matching to when you're doing that. And so this is essentially a way of generating an even more highly tailored kind of basis set of compounds that you're
Right.
actually looking to fit your data to, which will improve your matching rate and accuracy, I'd assume, by a lot, as opposed to trying to match to every single database compound that exists, like you pointed out early in the talk. So
Yeah, we think
really cool.
yeah. Thank you.
Mm-hmm.
I should just, for a little bit of a point of clarification, when you mentioned the Matrix and Batman, that's strictly accurate, but it's more accurate, I think, for David Wishart's basal kind of collection of things where
Yeah,
they
I think that was the one I was thinking of,
basal
actually. Yeah.
for urine, basal for serum and so forth, and that works great for that particular matrix. For Batman, you can take that approach, but Tim Ebels more takes the approach of just saying we can define a set of metabolites that we want to fit to it from the database without reference to the matrix per se. That's part
Okay,
of
the
the
next,
goes Batman.
okay, sorry. The next question is Brandon Plus. Brandon, are you still in the meeting? Please unmute.
Yes, I'm here. Sorry. Can you all hear me?
Hey,
Yes.
Brandon. Yeah.
Hey, so just to kind of preface real quick, I'm probably the most novice of uh, individuals here in the group with NMR. I came from a NMR lab at ASU.
We're all
And
learning.
yeah. But I mean, during my time there, I did a lot of work on plant metabolomics, mainly cannabis stuff, because it was during the time of the great cannabis hype, right? But at some point, like after my academics, I got into looking into some of these benchtop magnets that have been kind of coming up. And at the time, there, I think what the strongest one was a 60 megahertz. I can't remember what company, but more recently, the company Q Magnetics came out with a 125 megahertz magnet. I think we all understand the major limitations to benchtop magnets because, obviously resolution, naturally, sensitivity is always an issue as well, sample size. But they advertise this instrument with a HPLC setup, like kind of directly like funneled into the NMR unit. And I'm wondering if this kind of approach could help alleviate some of the headaches that come from trying to, make use out of benchtop NMR.
Brandon, that is a great question. That is not a naive question at all. We're really interested in that as well. And I think the answer is yes. There's a lot of promise with that. The thing that's interesting is once you make this metabolite basis set, it will be possible using tools like Gizmo to change what the spectrum it's hard to even talk about the metabolite basis set in in sort of an NMR correct way, because it's not strictly a spectrum. It's a derived spectrum, but they look like spectra. They act like spectra. So we could call them a spectra. These are our metabolite basis set elements. You can adjust what that looks like. These were collected at 800 megahertz, but you can adjust that according to the field. So you could, in principle, or not too hard in practice, adjust the look of this metabolite basis set to fit whatever field strength you want. There's some big advantages in collecting high field data to get the initial metabolite basis set. So actually, a lot of the fraction libraries that we're doing now are at 1.1 gigahertz, and that really helps. But you can downsample it to, say, 60 megahertz or 80 megahertz or whatever, and then use this just the same way to fit more of the blobs that you get from benchtop NMR. I don't see any reason at all why that won't work really well, to be honest.
Well, that's really promising and uplifting to hear. Since my academics, I've gotten into routine clinical diagnostics, and specifically, I do a lot of toxicology, drug screen analysis. Right, so it's kind of serendipitous. You mentioned starting to look forward towards working with urine as a matrix. I've been thinking about this for the past 2 years, how I could probably, kind of devise a method to work on doing the same kind of quantitative analysis on my LCMS I work on every day and transfer that over to, NMR. I learned quite a couple different very useful techniques for, sample preparation, and figured out a good couple sturdy ways to concentrate samples when needed. Especially at my time at Banner University, we did a lot of GCMS stuff, and that was part of the process of sample prep, drying it down and then reconstituting it into a solvent and then running it. But yeah, it's been that specific topic's been on my mind. I'm excited to see what comes out of your guys' work for urine.
Yeah, well, let me make one other comment about that. When you talked about toxicology and screening for things, the one thing that you have to remember is that the basis set, the metabolite basis set, it has what is in your reference sample. So if you have some pooled external reference control urine, that's what you're going to get for your metabolite basis set. And what you would see, in fact, we're interested in this as well. If you're missing some big concentration of something that's not in that basis set, it shows up in this residual. So the question really is, can we use the residuals in a way to infer what might be in there that wasn't part of the basis set? So we're interested in that. I'm not totally sure how well that would work, but there is a path forward to think about compounds that are not in your basis set and accounting for those in the residual. So anyway,
very cool. Thank you very much.
Welcome.
Now I'm glad that you have that picture on the screen. I have a question. I have a comment and questions about that. Because this is what I have been trying to challenge our tool as well. The residual as a guide to fit how good is the methodology of your decimation, even if there is no unknown. It becomes challenging because I have had a lot of examples where shifting the frequency, it's not about the amplitude that it is error, shifting the frequency with a fraction of a digital point fits it. So the question we have to ask is a fundamental question of, is the frequency you have by FT, which is limited by the digital resolution of the spectrum, or the computed frequency which came from the time domain, which is true, which is false? We don't know. I know what it is, but I don't want to challenge the group here. But I think it is the time domain is the truth, whereas frequency domain is based. Even if you have 512K point over 182 kilohertz, that's a resolution limit. Whereas we have seen fractions of the resolution limit. If we can move the frequency of that as a computer, we can match it. That means, should we be moving the frequency of the computer frequency or position of the computer frequency or move the position of the FT frequency. It's a question in order to match it. So residual becomes very dicey to actually take it up as seriously as we all end up doing.
Well, that's a super good point, Christian. I would tend to agree with you that in the time domain that's the real answer, but I think that there's even something more going on here because in practice, all of these samples, when we get into these big complex biological samples, they have different pH and salt and other kind of effects that will cause experimental changes in the peak positions. Some of them are small, some of them are big. Let me just say a few things. First of all of this is just out of the box Batman. And so I would recommend reading the work that Ebel's group have published on Batman. It's really helpful. But they have some pretty sophisticated parameters to account for peak adjustment, frequency changes in the fit. And that's actually one of the reasons why the histidine didn't work as well, because the peaks that didn't fit were outside of that range that we allowed it. So we still are not, we consider ourselves maybe sort of beginning intermediate users of Batman. We could certainly use it a little bit more effectively. But the residuals are actually a wavelet fit. Tim uses wavelets to account for the rest of the missing data. So, at least my limited knowledge of how that all works indicates that I think that this is it's not just a different spectrum, is what I'm trying to say.
Yeah.
It's a wavelet estimation of what's not accounted for. So
that representation that you have, the blue line, is not just a different spectrum.
It's not just a different spectrum,
okay,
right?
Fair enough.
Exactly. Yep.
Okay.
I do recommend looking into the Batman literature. They have a really good Nature Methods paper that I think, or Nature Protocols, one of the two.
Thank you.
Well,
any other questions? Anybody else have questions? You can unmute and ask now. If there are no other questions, thank you, Art. It's wonderful to.
Well, thank you, Chris.
Excellent,
Thank you, everyone,
talk. Thank you very
for
much.
hanging out. And bye-bye. Everybody stay warm this weekend. Okay.
Thank you very much, guys.
Okay.
Bye-bye.
Bye-bye.